No, thank you very much, and thank you for joining us today. So our next speaker is Caroline Juang, and Caroline will present Connecting Exponentially Increasing Burned Area to Fire Spread in Western United States Forests. And we, again, invite everybody to participate in the chat, which seems to be very lively right now. So Caroline, take it away.
Yes, thank you so much, and thank you for having me today for this session. I'm going to share my screen now. So thank you all for coming today. I'm Caroline Juang, and I'm a third-year PhD student at Lamont Doherty Earth Observatory at Columbia University. And I work in collaboration with Park Williams, who's at UCLA. And I'm really excited to present my research today, which is connecting exponentially increasing burned area to fire spread in Western United States forests. So I'll just dive right in. And I'm actually really excited to follow some of these talks about this current warming and drying trend in the Western United States. And shown here is the annual forest area burned in the Western United States. And as you can see, it is pretty rapidly increasing due to this trend, which is both human caused and also a natural variation in the climate. And in addition to that, in terms of the forest area, we have experienced a century of fire suppression, which has led to an increase in fuels in the Western United States from 1984 to 2020, which has then led to this massive expansion in burned area and in massive fires. And if I had 2021 in this record, you would actually see it go way beyond 15,000 kilometers squared that we saw back in 2020. About this trend, and if we plot the forest burned area annually against aridity in the atmosphere using vapor pressure deficit or VPD as a proxy on the graph on the left, we can see that there's a very strong exponential relationship where as aridity increases linearly, the amount of forest area burned increases exponentially. And this is a well-documented relationship and very well known, and also very appropriate for thinking about this session, which is climate extremes, because what does this mean for the future of forests and for the amount of fire we'll see in the future? However, what's not been documented robustly is why does this relationship occur where as as aridity increases linearly, forest area increases exponentially. So I wanted to investigate with this study with my collaborators this cause of this relationship. And to do so, I used a combined new database that my collaborators and I put together, which is a database of Western US fires combining the monitoring severity or MTBS database, which accounts for large fires greater than 4.04 kilometers squared, with 6 other government agency databases, including the US Forest Service, National Park Service, CAL FIRE for California, and others, in order to get a better picture of then smaller fires that are 1 to 4.04 kilometers squared from these government agency databases, and then MTBS, which accounts for those large fires. And as you can see, this database is unique in the sense that it captures a better picture of the frequency of fires every year. And so the number of fires has then doubled in this combined database, as opposed to just looking at large fires in the MTBS database. And on the map on the right, we can see the locations of these wildfires and their fractional forest area. So locations in red and forest area in green. And this is a map of over 18,000 recorded fires across both forested and non-forested areas. So I'm very excited to use this data, and this is actually a publication that's under review in GRL right now. And so then results-wise, what we learned by using this database is that, first of all, wildfire size is important to driving this exponential relationship, and then individual fires are important to driving this relationship. And below, looking at mean fire size versus fire frequency, this tackles the size component where we see that if we graph mean fire size on the y-axis against our linearly increasing aridity, we see that exponential relationship come out where it's really about fire size, versus if we take our database and look at fire frequency, it ends up increasing linearly. So even though both mean fire size and fire frequency both increase as a result of this drying and warming trend, we only get that exponential relationship through looking at fire size and like the spread of fires then. And then on the other hand, not shown is that the distribution of individual fires is super important to this relationship, where fires just generally occur on a power law distribution where there's many common small fires and a few very large fires in the Western United States. And as a result, because of that distribution, it's this exponential relationship that results. And diving slightly further into the individual aspect, and I only want to cover this section very briefly, but it is touched more in this paper under review, is that large fires have more potential for growth than small fires. So if we think about an elliptical fire model and a fire resulting from a single ignition point, as the fire increases in its radius linearly, we actually would see an exponential increase in the amount of area burned of that fire. And so then we looked closely at a separate database of daily fire spread by a collaborator, Jennifer Balch at CU Boulder. And I don't want you to interpret this graph too deeply because log scale is kind of weird, but as total fire size on the x-axis increases, so as the fire is getting bigger, then what we see is that the amount of new burned area for a single day is also increasing. So basically, as the fire is currently growing bigger, and each line on this log axis right here is a individual fire's growth over time, basically, then that fire size determines then how much new burned area it's going to get. And this positive slope here basically means that that this fire size is compounding based on the current size of the fire. So like a bank account and how bank accounts compound in interest, what we see is that the fire size compounds in size due to the current size of the fire. And that then is tied back to the exponential growth of fires on a regional scale. And so I want to end with this particular graph, which my conclusion is that basically this compounding growth rate of the largest fires, so because the largest fires have this compounding and greater potential for growing larger, this compounding growth rate then results in the exponential burned area and aridity relationship that we see across the Western United States in relationship to aridity. And so in this graph, we look at each individual year's decile of fires. So for example, in 1984, we look at the top 10% of fires and then the top 80 to 90% of fires, or then like the bottom 10% of fires. So we look at from 0 to 10 all the way to the top 10% of fires, and then take that size and then look at every single other year and then graph the trend lines for each percentage of fires. And what we see is that it's these largest fires that are contributing to the greatest increase in annual forest area burns over the entire study period of 1984 to 2019 using our databases. So in summary, we investigated the cause of the exponential burned area as a response to this linearly increasing aridity. And what we found is that it's wildfire size of individual fires that is the driver of this exponential relationship. We also see that large fires have more potential for growth than small fires. So as large fires increase in size, then that fire size at its current state determines a greater rate of growth and potential for growth. And then finally, it's the compounding growth of these largest fires that results in the exponential burned area aridity relationship. And it's important to note, like I mentioned, it's the power law distribution. So it's these individual fires, but it's these rare large fires that are the ones that have the greatest potential for growth and then result in the greatest growth across the Western United States on this massive regional scale. And so what's really interesting about this is that this relationship of exponential burned area to increasing linear aridity is a well-known relationship. This has been used in many statistical models and will still continue to be used. So the information that this relationship exists is not new. However, this research today provides a physical justification that it's this fire spread of individual fires that results in this relationship. And so this has future implications because we know that most of the Western US forests have not yet burned. So there's plenty of forests left to burn, there's plenty of fuel left for fires. And we know that there is this potential for greater warming and drying from both human causes and possible natural variability. So therefore, we want to know then how much more will burned area increase each year due to this warming and drying, and then therefore what kind of fire management and what kind of policy changes need to be made in order to prevent future fire risk. So thank you for listening to my presentation, and please feel free to reach out, and hopefully this publication on the right will be under review and be published in Geophysical research letters. Feel free to contact me. And also, I'd really like to thank my advisor and my collaborators, and as well as my fellow PhD lab mates and postdoc lab mates, and my funding sources. Thank you.
Thank you so much. Yeah, it was a great talk, and you do have some comments in the question box in the chat box, so hopefully that'll continue the discussion.